Alright, this video is going to be an overview of graphing polynomial functions. Now, making this in 2020, where we're kind of revisiting this at the end of the year, but if you're watching this in the middle of the year, some of these concepts may probably were already addressed, but this video is going to focus on all the things that go into graphing polynomial functions. So, factoring, synthetic division, intermediate value theorem, things like that could be found in other videos from Chapter 3. This one is going to kind of cherry pick things from Chapter 3 and just focus on graphing polynomial functions. So to start off, here's a example of a polynomial function, just in case you're not the best with vocab and you're not exactly sure what a polynomial function is. This here is a polynomial written in standard form. Alright, so a polynomial has variables raised to positive integer powers. And you're just multiplying and adding, and in standard form it's written from decreasing order of the exponents. You can also have it in factored form down here, and when it's in factored form you could tell a lot about the graph. When it's in factored form you could tell the x-intercepts, because the x-intercepts are what make y equal to 0. So if it's factored, any x value that makes any of these factors 0 will make y equal to 0. So for example, if you plugged in -4 in for x, then you would get y is equal to 0 because it's 0 times -7 times 9, which is equal to 0. So that's why you factor things, because of the zero product property. Anything times 0 is 0. You can also, we'll talk about how this tells you there's a bounce at zeros when zeros have an even multiplicity. We'll talk more about that later. So that's factored form. Factored form tells you x-intercepts. Standard form, don't sleep on that either. Standard form will tell you the end behavior, and we'll look at that. And so the end behavior is what happens as x gets really large. And also the y-intercept. The y-intercept occurs when x is 0, so that's why standard form is better, because if you plug in 0 for x, everything's going to simplify down to y is equal to -12. So that's just a brief overview, but just in case you don't know what a polynomial is, there it is. So a couple just general characteristics of polynomial graphs. They are continuous, alright? Continuous means that I can graph it in one fell swoop of the pen. Doesn't mean you have to, but it means there's no discontinuities. A discontinuity would be something where you'll see in the next slide where you have to pick up the pen to keep graphing, somewhere where the graph is not continuous. So holes, jumps, and asymptotes are examples of discontinuities. So the fact that they're continuous goes hand in hand with not having any discontinuities, and only smooth turns. So that these would be considered smooth turns, and it's just that's really important for calculus, these smooth curves. But other functions like absolute values, they don't have to have smooth turns. Okay, so here are some graphs that are not polynomials. Notice how on the left there's a sharp turn, a cusp if you will. That's an absolute value function, not a polynomial. And on the right you have a couple discontinuities as well. So first let's look at end behavior. So how can we determine what happens to f of x as y or x gets really large? And why does this happen? Okay, so let's look at y equals x minus 3. So y equals x minus 3 has a positive slope of 1. So you see that as x increases, y increases. So the end behavior for this would be as x approaches infinity, that's a bad infinity, y approaches infinity as well. And as x approaches negative infinity, okay, f of x approaches negative infinity as well. Now, let's look at another line. Let's look at a line with a negative slope. So let's look at maybe y equals negative x plus 2. Alright, so that has the opposite end behavior. I won't draw that out again, but as x approaches infinity, y approaches negative infinity, and as x approaches negative infinity, y approaches infinity. Okay, now what would happen if I multiplied them together? Well, if I multiplied x plus 2, if I multiplied negative x plus 2 with x minus 3, it would equal y equals negative x squared plus 5x minus 6. All right, so, and that, you could tell, has an end behavior where both sides go down. As x approaches infinity, y approaches infinity, negative infinity. As x approaches negative infinity, y also approaches negative infinity. Well, if we look at the two other functions here, their end behaviors are closely tied to the end behavior of them multiplied together. That's because in the red graph, all right, as x gets bigger, y is going to become a bigger positive number. And in the blue graph, which is written on the left, negative x plus 2, as x gets bigger, y approaches negative infinity. So you got positive times negative, that when you multiply them together is going to equal negative, which is why y is approaching negative infinity there. All right, and then same thing on the left. This approaches positive infinity, the red graph approaches negative infinity, so when you multiply them together, a positive times a negative is a negative. So that positive slope times a negative slope is going to give us a negative leading coefficient, which tells us that the graph is going to fall to the right. It has a negative slope to the right. And the even end behavior tells us that it's going to do the same thing to the left. All right, so I'm going to cut this video short and I'll explain this more in the next video.